The classes of MAXSNP mean F+pi1h and FPT. Kai and Chen were able to prove that large classes of important optimization problems have a corresponding parameterized problems, which are fixed parameter tractable. These problems are defined from subclasses of the collection of NP-complete, which are derived syntactically. The class MAXSNP was introduced by Papadimitriou and Yannakakis. Many important natural and well-studied NP optimization problems belong to this class. The class comes from consideration of the syntactic form of NP problems via Feigen's theorem below. Feigen's theorem is known in finite model theory as NP equals to sigma 1 to the 1. More precisely, the exact statement of the theorem is the following. For a more detailed discussion of second-order logic, we refer the reader to section 6.5, where the specific case of graphs is discussed in detail. Theorem 4.7. See Feigen's theorem. NP is the class of all problems that can be put in the form the set I such that there exists S in 2 to the n to the k for x in n to the p. There exists y in n to the q such that phi of I s x y holds. Here I is in subset equals to n to the m is the input relation. X and y are tuples ranging over n, which is equals to the set 1 to 3 until n, and phi is quantifier free. For instance, satisfiability can be written as there exists t for all c, there exists x. The following holds. P of Cx intersect x in T, union n of Cx intersect x not in T. Proof sketch. We sketch the proof, leaving the details to the reader. First, to get sigma 1 to the 1 is a subset equals to NP. Let C equals to the set A such that A implies there exists R psi, with psi first order as above. Then, given A, we can guess relations R and verify that AR implies psi, which is polynomial time. Conversely, NP is a subset equals to sigma 1 to the 1 as follows. Given an NP language L, and has a non-deterministic polynomial time machine M, we have that A is in L if and only if M accepts the encoding of A less than. One then needs only construct a first-order formula psi of less than x, which means x encodes an accepting computation of M on the encoding of A less than. Then L is equals to the set A such that A implies there exists less than there exists x host. Less than is the total order. Intersect psi. The key to the following is that some problems have a form that is simpler than the basic Feigen theorem. We can write 3 sets with one less alternation of quantifiers by assuming that the input consists of 4 relations C0, C1, C2, and C3, where Ci consists of all clauses with exactly j negative illiterals, with x1, x2, x3 is in Cj. Means that there is a clause with x1, x2, x3, until xj occurring negatively, and xj plus 1, xj plus 2, and so on until x3 positively. 3 set is then there exists T, for all x1, x2, x3, the following holds. The intersection of x1, x2, x3 in Cj, where the intersect is for the index j starting from 0 to 3, implies that the intersect of xi not in T, where the index of intersect is for all those I less than equals to j, intersect another bunch of intersection of xi in T, that is the intersection of the index I greater than j. The problems, such as 3 set, which can be expressed as there exists S for all x, psi of xgs, constitute a class called simple MP or SNP. For each pi in MP, one can then define the maximization version, MAXSNP. The maximization of the size of the set X such that there exists Y psi of XYGS holds, and the maximization is taken among all the possible S. The immediate relevance of all of the above to our studies comes from the following consequential definition. Definition 4.8, Papadimitriou and Yannakakis. A maximization problem Q equals to IQ, SQ, FQ, OPTQ is in the class MAXSNP if its optimum, OPTQ of X and IQ can be expressed as OPTQ of X is equal to the maxima of the size of the set of V such that psi of VXS holds, where the maxima is taken among all possible S, where the input instance X, which is the tuple U, P to the 1, P to the 2, P to the 3, and so on until P to the B, is described by a finite structure over the finite universe U, and P to the I is a predicate of arity, Ri, for some integer, Ri, which is greater than or equals to 1. S is also a finite structure over the universe U. B is a vector of fixed arity of elements in U, and psi is a quantifier-free formula. Despite the fact that Papadimitriou and Yannakakis proved that any problem in MAXSNP can be approximated to within some constant ratio, Aurora et al. Proved the beautiful result that MAXSNP complete optimization problems have no fully polynomial time approximation scheme unless P equals to NP. Because of this, we cannot use theorem 4.3 to demonstrate that MAXSNP problems are FPT. Nevertheless, Li, Kai, and Chen were able to establish the fixed parameter tractability of all problems in MAXSNP. Theorem 4.9, Kai and Chen. All maximization problems in the class MAXSNP are fixed parameter tractable. Proof. Let C be a fixed constant. Consider the following max C set problem. Max C set. Input. A set of Boolean formulas phi1, phi2, phi3, and phi each with at most C variables. Question. Find a truth assignment that satisfies the maximum number of the formulas. We first show that the corresponding parameterized problem, max C set equal, is fixed parameter tractable for every constant C. By Papadimitriou and Yannakakis, for any input instance X is equal to the set phi1, phi2, phi3, until phi of the problem max C set. The optimal value of X is at least n over 2 to the C. Moreover, since each formula in X has at most C variables, the total number of variables appearing in X is bounded by C times M. Therefore, the following algorithm demonstrates the fixed parameter tractability of the parameterized problem, MAXSNP set. Given a pair xk, where x is equals to the set p1, p2, p3 until pm, is an instance of the problem MAXSNP set, and k is an integer. We first compare the values k and m over 2 to the c. If k is less than m over 2 to the c, then xk is obviously a null instance. For the parameterized problem, MAXSNP set equal. If k is greater than or equals to m over 2 to the c, then we check all assignments to the variables in X to verify that whether the maximum number of formulas in X that can be satisfied by a single assignment is k. Since the total number of variables in X is bounded by c times m, there are at most 2 to the c times m different assignments to the variables in X. Therefore, the above algorithm runs in time big O of 2 to the c times m, which is bounded by big O of 2 to the big O of k times m, since m is bounded by k. M is equals to big O of k. This shows that the parameterized problem, MAXSNP set equal, is fixed parameter tractable. According to Papadimitriou and Yannakakis, every MAXSNP problem Q can be reduced to the problem MAXSNP set for some constant C in the following sense. There is a polynomial time algorithm that, given an input instance X in IQ of Q, it constructs an input instance X prime of MAXSNP set such that the optimum value for the instance X of the problem Q is equal to the optimal value for the instance X prime of the problem MAXSNP set. Therefore, the membership of the input instance xk for the parameterized problem Q equal is identical to the membership of the input instance x prime k for the parameterized problem MAXSNP set equal. Since x prime can be constructed from x in polynomial time, and the parameterized problem MAXSNP set equal is fixed parameter tractable, we conclude that the optimization problem Q in MAXSNP is also fixed parameter tractable. Since Q is an arbitrary problem in the class MAXSNP, the theorem follows. Lyman, Kai, and Chen also showed that an important class of minimization problems introduced by Colaitis and Thakur are fixed parameter tractable. Definition 4.10. Mean F plus pi1 of h. Define mean F plus pi1 of h. H is greater than or equal to 2 to be the class of all minimization problems Q whose optimum can be expressed as opt Q of x is equals to the minimization of the set of the size of S such that for all V, psi of V S X holds, and the minimization is taken among all partial S, where S is equals to U P0, and P0 is the predicate of arity 1 over the finite universe U, and the size of S denotes the weight of the predicate P0, i.e. the number of elements of the universe U on which the predicate P0 has truth value, and the psi of VSX is a quantifier-free CNF formula in which all occurrences of P0 are positive, and P0 occurs at most h times in each clause. Let mean F plus pi1 equals to the unions of mean F plus pi1 of h, where the union is taken among all the possible h which is greater than or equals to 2. The class mean F plus pi1 contains a number of well-studied minimization problems, including vertex cover and a large number of vertex deletion and h deletion graph problems. It is known that all minimization problems in mean F plus pi1 are polynomial time approximable to a constant ratio. Theorem 4.3 is not applicable to the class mean F plus pi1, since the problem vertex cover is MAXSNP hard, so it does not have a fully polynomial time approximation scheme unless p equals to NP. Theorem 4.11. Line-mean-kind chain. All minimization problems in the class mean F plus pi1 are fixed parameter tractable. Proof. Let Q be a minimization problem in the class mean F plus pi1 of h, where h is greater than or equals to 2 is a fixed integer. Then the optimum OPT Q of x for any input instance x of q can be expressed as OPT Q of x is equals to the minimization of the set of the size of x such that for all v, psi of v s x holds, and the minimization is taken among all possible s, where s is equals to u p0, and the p0 is a predicate of arity 1 over the finite universe u. V equals to v1, v2, v3 until vd is a vector over u of arity d for some fixed d. Psi of v s x is a quantifier-free CNF formula in which all occurrences of p0 are positive, and p0 occurs at most h times in each clause. We show below that the parameterized problem q less than or equals to is fixed parameter tractable. Fix an input instance x of q. Consider the formula f of xs is equals to the intersection of psi of vsx. The intersection is taken among all the possible v in u to the d, where u is the universe. Note that the formula f of xs is a quantifier-free CNF formula in which the only unknowns are p0 of u, where u is in the universe capital U. Moreover, according to the definition of psi, each clause of f of xs contains at most h unknowns p0 of u, where little u is in capital U, and all of them occur positively. Since the number of elements of the universe, capital U, is bounded by the length, the size of x, and the d is a fixed integer, the formula f of xs can be constructed from the input instance x in polynomial time. Now given an instance xk of the parameterized problem q less than or equals to, we first construct the formula f of xs equals to the set of C1, C2, C3, and so on until Cs, then execute the algorithm below. Algorithm 4.12. Weighted CNF of Fk. Input. A CNF formula F equals to the collection, the set of C1, C2, C3, and Cs, and an integer k, where each Ci is a clause in which there are at most h unknowns, or of the form p0 of u, where u is in the universe capital U and appearing positively. Question. Is there a finite structure S equals to u p0? K is greater than the size of S, and S satisfies F. If k is less than or equals to 0, then reject. If f is empty, then accept. Suppose that C1 equals to P0 of U1, P0 of U2, and so on to P0 of UC, where Uj is in the universe U, and C is less than or equals to H. For J equals to 1 to C, do the following. Make P0 of Uj equals to 1. Let F prime be the CNF formula obtained from the formula F by deleting all clauses that contain the occurrence P0 of Uj. Recursively call weighted CNF of F prime K minus 1. It is easy to verify the correctness of the algorithm weighted CNF F K if the algorithm weighted CNF of F K accepts. Then there is a finite structure S0 equals to U P0. The size of S0 is less than K, and the F of X S0 is equals to for all V such that psi of V S0 X equals to 1. Therefore, opt Q of X is equal to the minimization of the set of the size of S such that for all V, psi of V S X holds, and the minimization is taken among all possible S, and which is less than or equals to S0, the size of S0, which is less than K. Thus, Xk is a no instance of the parameterized problem Q less than or equals to. Otherwise, we should have opt Q of X is equals to the minimization of the set of the size of S such that for all V, psi of V S X holds, and the minimization is taken among all possible S, which is equals to the minimization of the size of S such that F of X S holds, and again the minimization is taken among all possible S, which is greater than or equals to K. Thus, Xk is a yes instance of the parameterized problem Q less than or equals to. Therefore, the problem Q less than or equals to can be solved through the algorithm weighted CNF. We claim that the running time of the algorithm weighted CNF Fk is bounded by big O of H to the K times the size of F. This is certainly true when K is less than or equals to 1. If K is greater than or equals to 2, then the loop body of step 4 is executed at most H times. Each time involves a recursive call weighted CNF F prime K minus 1, where the size of F prime is less than or equals to the size of F. By the inductive hypothesis, the running time of each call of weighted CNF F prime K minus 1 is bounded by big O of H to the K minus 1 times the size of F. Note that the length of the formula F is bounded by a polynomial of the length of the input X, which is independent of the parameter K, and H is a constant. Consequently, the parameterized problem Q less than or equals to is fixed parameter tractable.